So as Christoph said, I'm a philosopher from Clemson University in the United States. I'm also trained as an evolutionary biologist, so I'm kind of strange. And I want to, of course, thank the organizers for having the conference. I want to thank them for having a place where strange people like me can come. And I want to thank you all for showing up the morning after our big adventure last night. Those are all good things, right? I was a little bit worried that there would be 2 people in the room besides myself. So this is already a success. So for those of you who came to Hur, the meeting in Hur, you heard some of what I had to say about this basic sort of problem of definitional pessimism. So Carol Cleland has sort of made a career out of talking about why nobody should bother trying to define life. If anybody's read any of her papers and been taken with them, you really should talk to me. But basically, I think this is deeply misguided for any number of reasons. This is not that talk, so I won't talk about all the ways in which that's misguided. But just in a nutshell, we're never going to be able to make progress, and in particular come up with the kind of general theory of biology she says that we need to come up with, unless we at least try to define what life is. And unless it's actually impossible to do so, biologists have an obligation to be clear about the basic concepts that they're using. That doesn't mean that it's easy. It may even involve, God forbid, philosophers, but you have to be clear about the basic concepts that you're dealing with. And the bottom line is there's no really good argument that it's impossible to define life. In fact, there isn't even really a good argument that life is harder to define than any of the other weird biological categories that people argue about. Species, genes, these are all fuzzy categories, right? So this, in some sense, this is not a new problem for biology. So if you have read Cleland and thought, this is kind of reasonable, I like this, please talk to me. This is a philosophical emergency. We need to do an intervention. I will be happy to give you the paper that is forthcoming in IJA, and if you want to, I will talk to you over coffee and explain to you why this is a very bad thing. But I think part of the problem is that biologists tend not to like abstract conceptual discussion, which is where you quickly go when you start talking about life. And when someone comes along and tells them that they don't need to worry about this annoying kind of discussion, that it's pointless and impossible anyway, they like that. So you have a bias in favor of believing the person that tells you that you don't have to do what you don't want to do. But the arguments themselves are really pretty bad. Okay, that's all I'm going to say about definitional pessimism. Let me do sort of a little very, very simple philosophy of science. I won't get very complicated. If we think that science is an enterprise that describes the real world as opposed to just manipulating human concepts, right? Traditionally, the way to describe what is going on is science is identifying what's called natural kinds. So it's identifying objects or categories that actually exist in the real world independent of human beings. The way Socrates put it is, if you're defining something correctly, you're carving nature at the joints. You're not just making up classifications that make your life easier but have no meaning for the real world. And typically, philosophers talk about natural kinds in terms of specifying necessary and sufficient conditions. So you specify necessary and sufficient conditions, and you know you've got the natural kind right when those conditions cleanly delineate a category and nobody argues about the category. Then you've got it right. And Cleland and others say, you can't do that with life, therefore there's no point in trying to define life. Of course, there's another move, which is to say you shouldn't be doing that, but we'll get to that in a second. Biological kinds, I think, are fundamentally different. There are actually reasons to think that natural kinds language, the way classic philosophy of science talks about it, doesn't work even with paradigm examples like chemical species, but I won't go there. Let's just talk about biology, right? For biological categories, I don't think you're really going to be able to succeed in using necessary and sufficient condition language, whether they're natural kinds or not, right? The bottom line is biology blurs all lines, right? Anybody who's ever tried to identify an actual organism using a field manual is aware of this problem, because the thing never looks like the picture in the field manual, and you end up flipping back and forth between 3 different pages trying to figure out if it looks a little bit more like that or a little bit more like this, and oh, that's got a seasonal variation, damn, and you're never really quite sure. You have to call in some expert to really solve the problem for you, and even then sometimes they'll say, yeah, I'm not entirely sure on that picture, I'd have to examine it in the lab. So biology, this is just the way biology works, and the reason it works this way is because biological categories are produced by evolution. Evolution is an inherently stochastic process that's driven by variation. So if you have an inherently stochastic process driven by variation, you should not expect that it will produce clean categories that can be delineated with necessary and sufficient conditions. That's just a strange thing to do. I think that's a hangover of physics. Philosophy of science used to be concerned with physics, and it sort of added biology later on, but whatever, right? And that doesn't mean, by the way, that it's impossible to define categories. And I will just infect you with a very old philosophical paradox called the Sorites paradox. How many stones does it take to make a pile? But if you have one stone, not a pile, right? If you have 10,000 stones,
it's a mountain.
Well, okay, we could talk about its ontological status. It's definitely some sort of pile, right? It's very difficult to give a definitive answer for where it transitions from being a group of stones to a pile. That doesn't mean that there's no meaningful distinction between the two, right? And that's essentially what you have in a lot of biological categories is the boundaries are fuzzy, but the concept is importantly different from other concepts. People in science, typical researchers in science, they have slightly different kinds of things that they're interested in pursuing. So the biochemists are interested in one set of problems and the thermodynamics guys are interested in another set of problems. And when you have different things you're interested in answering, you ask slightly different kinds of questions. And just as a sociological phenomenon, we tend to exaggerate the differences between similarly positioned researchers. So if you have three different people who are all working on concepts of life and they have slightly different conceptions, they will, as a general prediction, tend to accentuate the differences between themselves. If you want to make this biological, this is competitive exclusion. So you get the same thing in ecology. Organisms that are most similar to each other tend to compete the strongest. This may not work with this audience, but when I teach my classes, I make the analogy of college football teams, right? The rival is always the school just down the road that is essentially identical to you in every way except they're them and we're us and we hate them. And it's like that, right? That's the way scientists tend to do. And this leads to all kinds of historical debates where in retrospect you look at the debate and you say, well, these are both just variations on a theme, but people hate each other and they got famous writing papers talking about why they're right and the other guy's wrong. And Tonus the other day talked about mutationism, which was originally presented as this fundamental alternative to Darwinism. Then there are the punctuate equilibrium wars that come along. These are examples of this kind of dynamic where people are taking what's essentially a flavor difference or an emphasis difference and then trying to make it into a difference of kind. Okay, so I think, having given Cleveland a hard time, I have some obligation to at least try my hand at coming up with a positive account. This is very much a work in progress, okay? But I would argue that we really have to have some kind of core concept on what we mean by life. If we really don't have a core concept on what we mean by life, then much of biology is deeply, deeply confused. And I think that's probably not accurate, right? And then what we want to do is we want to try to come up with a core concept that everyone can agree on that's very general, right? And then allow individual researchers to specify that core concept to fit the particular kinds of questions that they're asking in their particular subdiscipline. That's the basic idea. And if you're interested, Mishler and Brandon back in '87 have this classic paper where they do this with species concepts. And what they basically argue is, look, the one non-negotiable thing when it comes to a species is species must be monophyletic, right? You have to have monophyly. That we cannot compromise on. But once you have a monophyletic grouping, you can fiddle with the boundaries of that grouping in lots of different ways, depending on what your interests are. Ecologists want to talk about ecological mechanisms for maintaining species cohesion, et cetera, et cetera. So there's no reason to think that there has to be a single unique way of describing a particular species, if by species you mean something very specific. But there has to be agreement on the larger grouping or you're lost, right? I think maybe we can do something like that when it comes to life. And we'll see in just a second. So I apologize because right now I'm going to run through what I consider to be plausible categories for definitions of life very quickly. I will probably do a very bad job. I don't mean to insult anybody as I do this, but I'm just going to very quickly sort of give you a 50,000 foot view of these positions, which I argue is the view you want if you're trying to develop a core concept. You don't want to get too bogged down in details, and I have a tendency to do that just like many of you. So there's the thermodynamic kind of approach, right? Where, as we heard a little bit earlier, the idea is life is some sort of dissipative structure embedded in a non-equilibrium energetic environment, right? And then essentially energy is flowing through the system, et cetera, right? Sociologically, Physicists in particular like to talk about this kind of stuff. It basically shows that living systems are just an extension of a more general category of physical systems, so it gives them this generality with a capital G, and it allows them to play with mathematics, which physicists like, right? But I'm not, that's a joke, but there's some truth to it. I think you'll see. I'll make jokes about other people in a second. But there is also something I think importantly correct about this way of thinking about things. It is in fact true that life consists of dissipative structures, right? It's not true that all dissipative structures are alive, but it is true that all living things are dissipative structures, and that is an important perspective. Adopting that perspective with respect to certain kinds of problems actually gives you insight. So we talked the other day about if it's the case that Titan is at thermodynamic equilibrium, you're not going to get life there. It doesn't matter what kinds of chemical components you have, you're going to have some kind of energy gradient in order to generate life. That seems true, and you might not realize that if you're focused on the biochemistry and the importance of liquid water or something like that. So there's a truth here, it's just not the whole truth. Then there's the sort of general category of metabolic people that like to talk about autopoiesis and autocatalysis and biochemical networks and all that kind of stuff. Something like life is a self-sustaining set of perhaps chemical, perhaps not chemical agents, right? Sociologically, origins of life people in particular like this kind of approach. And part of the reason why they like this kind of approach is if you're doing origins of life, then by definition, your job is to draw a line. Non-living, living, ta-da, right? And so you have to be able to say, right there, right, that's where you get the autocatalytic set, right? And it lets them speak about biochemistry, which typically they really like to do. They like to draw the reaction networks and all that complex stuff and talk about pyruvates and all that. But again, there's something objectively true here, right? There is, I think, a really critical qualitative discontinuity between a non-autocatalytic set and an autocatalytic set. If you have an autocatalytic set, you have something which is sufficiently cohesive that it can be called an individual. Now, biologists maybe don't use that term. We could give a technical term, we can give a technical description of individuality, that's not important. But in particular, that allows you to talk about certain kinds of changes within that system counting as adaptations. You can't have an adaptation unless there's an individual whose interests that change serves. And you don't get individuals and interests unless you have at least an autocatalytic set. So this does seem to be a minimum condition where you get an important qualitative change. Evolutionary definitions, this is the one that I'm initially drawn to, not surprisingly, because I'm trained as an evolutionary biologist. So that should tell you something right there. For a long time, I thought evolutionary definitions were the way to go, and everything else was just detail. I'm sure that there are people out there that would say the same about evolutionary definitions. But essentially, it's something like a chemical system that's capable of Darwinian evolution. That's the sort of basic NASA definition, as it's so called. Sociologically, organismal biologists tend to like this because what they do is they study organisms in this grand sweep of evolutionary diversity, and they like to be able to wave their hands and talk about biospheres and all that kind of fun stuff. And they get to talk about birds too. I don't know what it is, but organismal biologists always like to talk about birds. I'm a bug guy myself, but I understand the tendency. But again, there's something objectively true here, right? So until you get robust evolution by natural selection, you're not going to get the enormous diversity which is characteristic of living systems. You're just not going to get it. So an autocatalytic set, we could argue, is capable of evolution with a small e, and if you wait a really long time, it may get to places where you want it to go. But there's a bit of a phase transition as well when you have actual populations and robust inheritance mechanisms and all that kind of good stuff. And if it weren't for that, there wouldn't be intelligent beings to care about this, then there wouldn't be anybody that really would be caring about autocatalytic sets. So everybody, biologists and everybody else, wants nice, clean categories. That's a nice ideal to shoot for, and I'm all in favor of trying to get nice, clean categories as long as you possibly can, right? But there's not going to be, I think, a single concept of life that fits all the different specific uses that biologists want to make of it. That is true. And in that sense, the pessimists have a point, right? If that's what you want, if you want a single one-size-fits-all definition of biology, of life that can be applied to every specific biological problem, you're not going to get that. But I just would say, then that's not what you should be trying to do. What you should be trying to do is something more general, right? So we're going to have to allow people some flexibility to draw particular lines around living and non-living systems with some degree of plurality. So somehow we have to figure out how to do that. And this is my very tentative suggestion for how to do that. So I think that life is something like this. life involves any process that's capable of producing adaptive complexity. Okay, the adaptive word is important because if you don't have adaptive, then you get into Shannon information concepts of complexity, and it has no biological meaning, and that's not what we want, right? So you, at the very least, you have to have an autocatalytic set in order to qualify any change as adaptive. And if you're talking about increasing complexity, you're going to be forced to talk about population dynamics and large-scale trends and all that kind of stuff. You can take a metabolic spin on this question, right? And you can say, well, my goal is to figure out what the absolutely minimal system is that is capable of doing this in some sense, right? And then you can figure out what regimes would produce such a system on Earth, what regimes would produce on alien planets, et cetera, right? Evolutionary sort of spin on this is, how do populations of life forms actually produce larger amounts of diversity than an autocatalytic set is capable of, under what circumstances, what kinds of things prevent diversity, et cetera, et cetera. They're basically two sides of the same coin, right? What they're both talking about is increases in adaptive complexity or adaptive diversity. In particular, what they're really doing is they're talking about different timescales, right? So if you have a metabolic kind of focus, you're probably talking about individuals dealing with relatively small scale environmental challenges over small time and space scales. And if you're talking about evolution, you're talking about populations dealing with large scale problems over larger time and spatial scales, but they're both dealing with generation of adaptive complexity. So we all like to hide our shortcomings from ourselves, from other people. And one of the ways of doing about that is to sort of develop a rule of thumb way of thinking about the world. And I think, because this is the way I used to think about it, I think this probably is an accurate way of describing the way lots of people think about life from their own little perspective. So they like to sort of believe that their view is sufficient in some sense. Now they'll grant that it doesn't explain everything, but it's more or less sufficient, and then they insert sort of a hand wave, right? So the way to think about this is, once you have fill in the blank, it's all downhill, right? And then different people fill that blank in different ways. So if you're a thermodynamics guy, you say, well, once you've got energy flow across an energy gradient, it's just a matter of time before you get autocatalytic sets. And that's, of course, that's all detail I'm not really interested in. The metabolic guys will say, well, once you have autocatalysis, then of course you're going to get population structures and natural selection, heritable. Yeah. That's all going to happen later on. It's just a matter of time. And of course, the evolutionary guys, they'll say, well, we've already got population structures and everything, and all that stuff that happened before. Well, yeah, of course you need that stuff, but it's not like that's really important. That's just precursor stuff that we can just kind of assume into existence. They're all making legitimate points. There are senses in which each of these is sufficient with respect to certain sets of assumed conditions, right? It all depends on what it is you want to assume into existence and how much you're willing to wait to get the next level of organization, right? If nothing else, and I think this is an important point that I haven't really thought through very carefully, if nothing else though, whatever you might think about the sufficiency of these, you have to at least grant that they all depend on a heterogeneous environment. Right, so if nothing else, they're all assuming a heterogeneous environment, and probably a fairly specific kind of heterogeneous environment, right? Which is just, all of them take as just a given background condition, and that's not necessarily the case. So I think maybe the way to think about these different sorts of ways of thinking about life is what they really are is they're all about adaptive complexity, about the generation of adaptive complexity, but they all point to a particular transition in the capability of generating adaptive complexity, right? A discontinuity in the rate at which adaptive complexity is generated, right? So essentially what you have is an increase in adaptive complexity. Once you have autocatalytic systems, it's much, much faster to accumulate adaptive complexity. Once you have evolving populations, it's faster still. There could be endpoints both above and below this. So if you want to get even below the level of thermodynamic gradients, you might be able to make an argument that the evolution of order in the universe, whatever that means, is a certain kind of adaptive complexity. You might be able to go on the other end and argue that there are other major transitions past the acquisition of evolution by natural selection. For example, the acquisition of learning and culture, which allows for cultural evolution, which proceeds at a faster rate, yada, 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 right? Now, a couple of implications that I'm just going to sort of wave at and I won't talk about in great detail. First is that this way of thinking about life, it should be really clear. This is a functional account of life. It's not a structural account of life. One of the things that Carol Cleland says frequently is that we don't know for sure that life doesn't have a structural basis, which of course is true. We don't know for sure that life doesn't have a structural basis. I personally find that extremely implausible, that there's some secret molecule or secret molecular structure that we haven't discovered yet that explains life. I guess it's possible, but I find it implausible. So if you have a functional account of what a thing is, what that means is the material out of which that thing is composed is irrelevant, right? So if you're a functionalism in philosophy of mind, you're talking about a mind in terms of a relationship between parts, and it doesn't matter if those parts are made out of neurons or they're made out of beer cans and string. As long as the formal relationships are correct, then it meets the criteria. So it doesn't really make any difference from this point of view whether life is composed of nucleic acids or something else. It may make a difference that there's a heritable mechanism, and that heritable mechanism has certain properties, and it may be possible that certain kinds of specific chemical reactions are necessary, like redox reactions. Maybe it really isn't possible to have life without redox reactions. But that's an empirical question, right? The property of being alive, if you think of it this way, comes in degrees. Right? So it's not an either-or proposition. If you think of these different endpoints as phase transitions and the capacity to produce adaptive complexity, then what you have is you have systems that are more and less alive, right? So an autocatalytic set that still hasn't come up with a heritable molecule, doesn't have population structures and like that, it's alive. There's an important sense in which it's alive, but there's also an important sense in which it's less alive than a population of organisms that has more sophisticated heritability mechanisms and all that kind of stuff. And this is something that I've been toying with a little bit lately that still makes me nervous to talk about because it's very strange. But I think that the universe and the life in it may progress, and I should progress, right? I'm not sure of another word to use for this. I don't like the P word, but it is handy at getting a sense of what we're talking about, towards something like universal attractors and possibility space. So the idea is that forget weird metaphysical forces, right? It could be that there are universal patterns to the acquisition of adaptive complexity that tell a large-scale story about evolution. You're not going to see that, at least not clearly, by looking at evolution on a single planet, because you just don't have enough statistical data. But if you could see evolution play out across many, many planets over large timescales, it may very well be that there are these large-scale patterns. Whether or not that's true, I'm not really sure, but I think it's an intriguing idea that sort of is suggested by some of this kind of stuff. So here's my hope, and we'll see if I pulled it off. This is my favorite quote from Enrico Fermi. Before I came here, I was confused about this subject. Having listened to your lecture, I'm still confused, but on a higher level. So I'm hoping I haven't really, well, it would be great if I answered all your questions about life. I'm not thinking that's happening, but maybe you've said to yourself, this is actually sort of intriguingly confusing as opposed to just annoyingly confusing. And so on that, I will put up this announcement about a workshop that I'm doing in Clemson for your information. And if anybody has any questions, you can fire away.